In this lesson, we will discuss the maximum power transfer theorem. It is a theorem of great practical importance. If you have a circuit with a number of independent sources and other linear components such as resistors and control sources, and you have access to two of its terminals, the question is, how do you extract the maximum power by connecting a resistor, a load between these two terminals? Okay. So, what we will work out is the condition for maximizing the power that can be drawn from these terminals. It is known as the maximum power transfer theorem. We have a network N with independent sources, linear resistors and linear control sources, self-contained. So, all the controlling quantities are within the same circuit N, and we have access to two of its terminals, 1 prime. We can connect a resistance RL between 1 and 1 prime, and we are allowed to vary RL, and we are required to find out at what value of RL we can draw the maximum power from the circuit. That is, at what value of RL will maximum power be dissipated in RL and how much that power is. Okay. Okay. Now, we know that every network, every circuit for which two terminals are accessible can be modeled by either the Thevenin equivalent, a voltage source VTH in series with a resistance RTH, or the Norton equivalent, a current source IN in parallel with a resistance RN. So, we will use these models. Okay. We do not want to deal with the specifics of the circuit, but we know that all these circuits can be reduced to this model or that model. So, we will consider one of these models to find the condition for maximum power transfer. We can use either one, the answer will be exactly the same with either case. Okay. So, now if we have a voltage source VTH in series with RTH, this part is fixed anyway, because what we are allowed to vary is the load RL. So, as RL is varied, when does it draw the maximum power? That is what we want to find. Okay. Now, what is the power dissipated in RL? PL will be equal to the voltage across RL times the current through RL. Okay. The voltage across RL from voltage divider expression is VTH times RL by RL plus RTH. The current through RL, we have VTH across RTH plus RL. So, it will be just VTH by RL plus RTH. The power PL, which is the product of the two, will be VTH square RL by RL plus RTH square. Okay. Now, of course, to maximize a function, we know that we can differentiate the function and set it to 0. At least that will find the extremes of the function, whether it is maximum or minimum, and by finding the second derivative, you can figure out whether it is the maximum or minimum. Okay. Now, by differentiating this with respect to RL, which is our variable here, which is what we are allowed to vary, we have VTH square, which is a constant as far as we are concerned, and the denominator will be squared. We will have denominator times the derivative of the numerator, which turns out to be RL plus RTH square times the derivative of RL, which is 1, minus the numerator RL times the derivative of the denominator, which is 2 times RL plus RTH. Okay. So, this whole thing turns out to be VTH square times RL plus RTH, RTH minus RL. Okay. And here we have RL plus RTH to the power of 4. Okay. Now, it is very easy to see that this goes to 0 when RL equals RTH. Okay. When RL equals RTH, the derivative goes to 0. So, that is when the extreme must occur, and it turns out that that is the maximum. Okay. What does it say? If the load resistance equals the Thevenin resistance seen across the two terminals 1 1 prime, then it draws the maximum amount of power. Okay. This condition is known as matching of the load to the source. The source has some internal resistance, which is RTH. Okay, that is the equivalent resistance, Thevenin resistance of the source. And if you have a load which is exactly the same value, then you draw the maximum power. Okay. Now, how much is that power? So, if this is the case, the current here will be VTH by 2 RTH, and the voltage across this will be just VTH by 2. So, the maximum power that can ever be dissipated in RL as you vary RL for a given source is the product of this voltage and current, which is VTH square by 4 RTH. Okay. Notice that this is a property of just the circuit. Okay. The load, when it is arranged to draw maximum power, its resistance will be equal to the source resistance. So, the maximum power that is dissipated in the load will be equal to VTH square by 4 RTH, and this is known as the maximum available power from the source. By source, I mean this part, the combination of VTH and RTH, which could be by itself like that. That is, you could have a voltage source in series with a resistance, or it could be a representation of a very complicated circuit. We know that any complicated circuit can be represented in this form, a voltage source in series with a resistance. Okay. So, whatever it is, the maximum available power from the source is this much. That is, if you do all you can to maximize the amount of power drawn from the source, this is what you will be able to draw. Okay. So, in summary, if you have a source which is represented by a voltage source VTH in series with a resistance RTH, then to draw maximum power from that, you should connect a load resistance which is exactly equal to RTH. That is, you should match the load to the source, and the amount of power you can draw, which will be the maximum available power from the source, is VTH square by 4 RTH. Okay. So, here is the statement of the maximum power transfer theorem. For a given source, when I say given source, the Thevenin voltage and the Thevenin resistance are given, maximum power can be drawn from it when the load resistance equals the Thevenin resistance of the source. I will call it the source resistance. RL equals RTH, and the maximum power drawn, which is defined to be the available power of the source equals VTH square by 4 RTH. Okay. This is the available power. Okay. Now, I made some implicit assumptions here. I assume that RTH was positive and RL is also positive. That is, this is the case with many sources such as an antenna. An antenna can be represented as a voltage source in series with some resistance which constitutes the impedance of the antenna, and then the load, it is always dissipative. So, it also is a positive resistor. Okay. So, under these conditions, when you make RL equals RTH, you draw maximum power. Okay. This can also be derived in a slightly different way. The expression for the power was VTH square by RL plus RTH square times RL, which can be rewritten as VTH square by RTH, RTH RL by RTH plus RL squared, and I will further rewrite this as VTH square by RTH times square root of RTH RL by RTH plus RL, this whole thing square. And finally, taking the square root term into the denominator, we will get VTH square by RTH 1 by square root RTH by RL plus square root RL by RTH square. Okay. Now, if you observe the denominator, that is this one, it is of the form x plus 1 by x square. Now, this function x by 1, now this form x plus 1 by x may be familiar to you. Okay. Now, as x increases, the first one increases and the second one decreases, and if you try to minimize the value of this, you will find that the minimum will occur when x exactly equals 1. Okay. So, this has a minimum when x equals 1. Okay. When x tends to 0, this one goes towards infinity. When x tends to infinity, this one goes towards infinity. Okay. In the middle somewhere it will reach minimum, and it turns out that it will be when x equals 1. You can work this out for yourself. Now, if you see the denominator of this expression, it is of this form x plus 1 by x squared. Now, to maximize this function, the power in the load, we have to minimize the denominator. Okay. Remember, RL is only in the denominator, nowhere else in the expression. So, we have to minimize the denominator, and that will be minimum when x equals 1, that is, each of these terms equals 1. You can think of one of them as x and the other one as 1 by x. Okay. In other words, the maximum of PL, which occurs when the denominator is at its minimum, when square root RL by RTH is 1 or RL equals RTH. Okay. So, another way of deriving the same result. Okay. Now, let us explore this a little bit further. This expression PL being VTH square times RL by RL plus RTH squared. Okay. If you plot PL as a function of RL, this is what you will see. Okay. If RTH is positive and RL is restricted to be positive, then this function will be maximum when RL equals RTH, and then for both RL equal to 0 and RL equal to infinity, the power falls off to 0. Okay. For RL equal to 0, the load is a short circuit, there can be no voltage across it and it does not draw any power, it does not dissipate any power. Similarly, when RL equals infinity, it is an open circuit, there can be no current through it, and again there is no power through RL. Now, if you allowed RL to be negative, what happens is that when RL equals minus RTH, you have a short circuit across the voltage source. The series combination gives you 0 resistance. Okay. So, that gives you the maximum possible current, that is infinite current through RL. Okay. And in fact, RL will be delivering power instead of absorbing power, and the power actually goes to infinity when RL equals minus RTH. When it becomes more negative than minus RTH, it again comes back to 0. Okay. So, here I have assumed that RTH is more than 0, and then this will be when maximum power is absorbed in RL. Okay. And if you say maximum power absorbed or delivered by RL, the maximum power will be delivered when RL equals minus RTH. Okay. But of course, this is not a very useful result, because this means that RL itself is delivering power, and to arrange for that, RL cannot be a physical resistor, but equivalent of some complicated circuit with sources inside and so on. Okay. So, this is not a very useful result, but I just wanted to highlight that it is possible to have infinite power also, but then it will be infinite power being delivered by RL. Okay. When RL exactly equals minus RTH, the current in the loop goes to infinity and you have infinite power as well. Okay. But the result of real significance is this: when RL equals RTH and you have the maximum power absorbed. Okay. An example of this happens when you have an antenna. Antenna can be represented as a voltage source in series with a resistance. Many standard antennas have a 50 ohm internal resistance. So, you have a voltage source in series with a 50 ohm resistance, and to draw maximum power from that, your circuit must appear like a 50 ohm resistance. Again, even this load resistance is a representation of the input of your circuit. It may or may not be a physical resistance. If it is a physical resistance, power will be dissipated in it. If it is the equivalent of something, power will go elsewhere. Okay. But to draw the maximum power from an antenna which has a 50 ohm internal resistance, your circuit should also present 50 ohm resistance. And those of you who will go on to study RF circuits later, you find that a lot of effort is expended on in trying to make the input of a circuit look like 50 ohms. Okay. And as a very last thing, I just want to touch upon something. I won't discuss. This scenario is sometimes confused with the scenario that we already discussed. That is, let us say we have a source Vs and its source resistance Rs. okay, and you connect a load to it. Exactly the same situation as before. I simply change the symbols around, that is all. Now, let us say that you vary RS, not RL. As you vary RS, what is its value when maximum power is absorbed in RL. Okay. I won't work this out, you can do it yourself, and you can do it by differentiation or by thinking about it in any other way. And of course, you can for now assume that all resistances are positive, okay, they are non-negative. Think about it, the answer is very simple, but do not confuse this situation with the other one where we were varying RL and trying to find when the maximum power is absorbed in RL. Okay.